Yesterday, we talked about how Earth's curved surface allows for differential or uneven heating. Today, I'm going to explain two other factors that contribute to uneven heating. But first, there's something I need to tell you guys about why this uneven heating is a problem for Earth's atmosphere. You see, the sun, what am I looking at? I don't even know what I'm looking over
The
there.
floor.
The sun's energy comes in from space, right? And it heats the planet's surface. I know that the sunlight comes through the atmosphere before it touches the surface. That's okay. But that's not necessarily what heats up the atmosphere. What really heats up the atmosphere is that Earth's surface, no matter what kind of surface it is, it does absorb some of that heat. But like I told you guys before, matter doesn't like being hot. It doesn't like having extra thermal energy. So Earth's surface tries to send that thermal energy back out. It's like, ew, I don't want it, gross. Now, when Earth's surface sends out that absorbed energy, it has no place to go but into the atmosphere. So we'll have more on that later, how that works. But what we want to focus on right now is that some parts of the Earth do heat up faster than others, and that creates differential heating. Why do some places heat up faster? Well, yesterday I told you that the sunlight's direct at the equator. I knew what it was called. Okay, and it's more spread out, less concentrated and indirect near the top. But I'm going to show you a couple of other things. Okay? First, I want to show you these two surfaces. Very scientific equipment I have here. Okay? Here is a dish filled with sand. It represents parts of the planet's surface that are covered with dirt and rocks and this and that. Here, this little plate, I don't know if you can tell, is filled with water. Now, you go for a day at the beach. You're walking around barefoot, okay? And it's a hot, sunny day. You're on the sand, and you're like, ah! It's really hot, and it burns your toes. So what do? You make your way over to the water, and you put your feet in that. And the water feels cooler. Here's the deal. The sand and the water have both been exposed to the same amount of sunlight all day long. But they're different substances. This sand, okay, is solid. This water is liquid. This sand is darker in color. The water is clear and colorless. The sand is kind of dull, and if I shine a light on it, I don't really get a lot of reflection back. In the water, I can get a glint or show that the surface is reflective. Being these two different surfaces, okay, means that the Earth is being heated up more over here. The Earth's surface is being heated up less over here. Okay? That means that they both absorb energy, but over here there's more energy being sent back out because this doesn't want all of that. So the air above the sand is heated up more than the air above the water. Okay? Now, I want to show you on Earth. Okay? The darker surfaces, obviously, that's the land. This is all the ocean, right? Ow! This hit my hand. The ocean, just like the water here, okay, it heats up slower. So that it keeps the air above it cooler. On land, represented by the sand, okay, the air heats up fast. The surface heats up faster, and that keeps the air warmer. Okay? Now, there is something else that I want to show you. Hey, okay? The curvature of the Earth creates another differential heating besides what I talked to you about yesterday. Think about it. The light's traveling in from space. Okay? Notice how it does get to the surface at the equator first. Now, it still has to get to the North Pole, but look, it has to travel through all this atmosphere at the North Pole where it travels through a little bit of atmosphere at the equator. It's hard to see that in this model, so I'm going to give you a bad Rolex analogy. Okay, so you look at these two models I have set up here. In this bad rules analogy, we have two different car washes. We have a short car wash that goes through here, and we have a longer car wash, which is 3 times longer, going through this way. Now, imagine if we have a car that is covered in dirt. Okay? And in this analogy, the dirt represents the sun's thermal energy. If the car goes through the small car wash, oh my God, what are we doing? It's a convertible. No, this is so dumb. The whole inside's ruined. Because it goes through a small car wash, a lot of the dirt is allowed to get through. Or in other words, a lot of the sun's energy is allowed to get through. Now you put these geniuses, put the dirt back on their car, all the dirt, have them go through the longer car wash. We didn't learn our lesson. No, we're still in it. This is ridiculous. Okay. Because the car wash itself is longer, a lot more of the dirt gets trapped inside here because there's a lot more car wash for it to go through. In the analogy, it's the sun's energy. Less of the sun's energy can get through when it travels through more atmosphere. Okay? So let me show you what that looks like on the map. All right. So, when you look at this image, okay, you see here this dark ring is representing the atmosphere, and this is the sun's energy coming in from space. As the sun's energy passes through the atmosphere near the equator, okay, you can actually see that on this model, the sun's energy is traveling through about 1.5 centimeters of atmosphere. On the same model, if you go to the top by the North Pole, you'll notice that the sunlight has to travel through 3.5 centimeters of atmosphere. So the dumb rolls analogy talks about how this is like the car wash. You see? The short car wash gets more sunlight through, meaning this is going to be heated more. The longer car wash represents the longer distance the light has to travel in through the atmosphere, meaning that more sunlight is going to get absorbed, scattered, or filtered, or even radiated back into space. Okay? Now, combining all these things, I talk a lot, causes the Earth to get heated differently. All right? Thank you very much.